Okay, hello and welcome to another Go3 online session. So what we'll be doing today is basically the charging and discharging of capacitors. So for A level, the charging and discharging of capacitors. So first thing that I want you to understand is that you know that our capacitor is also called a condenser. Our capacitor is also called a condenser, and I've said it earlier that basically what a capacitor does is that it stores electrical energy. Are we clear about that? So before it can be able to store electrical energy, you have to be able to charge the capacitor. So for example, just like your power bank, if your power bank can store any energy, you have to charge your power bank. And then also if you also want to use your power bank to charge another device, that means it's what? Discharging. So basically what I want to talk about right now is charging and discharging of capacitors. We'll solve some questions on it and we'll also solve some complex questions on capacitors as well. So basically what I want to understand is that we'll be dealing with the charging and discharging of our capacitors. So now basically dealing with when it is in an RC circuit. Now the R refers to as our resistor and C is our capacitor. So I'll use a simple diagram to allow us to understand this phenomenon. So the resistor, we have a capacitor, we have our battery, a cell, we have a key, so this is our resistor, our capacitor. Let us say the EMF of our battery is 12 volts. Now this is the key. So now basically, one thing you should understand is that what we are trying to do here is we are trying to charge this capacitor. We are trying to discharge this capacitor. So let us deal with the charging aspect first. So I'll be writing the formulas over here. So basically, when this key is open, the potential difference or the voltage for your resistor will be maximum. So the voltage here will be 12 volts. While for the capacitor it will be 0. Are we clear about that? So the voltage for your resistor will be 12 volts, while for the capacitor it will be 0 because the key is still open. Now when we close the key, for example, when our time is still 0, that is basically before any current starts moving around, your resistor will still have a charge of 12 volts, your capacitor will have a charge of 0 volts. But when your capacitor is fully charged, this the voltage for your resistor will reduce to 0, while that of your capacitor will reduce to 12 volts. So why is because after your capacitor is already fully charged, your current is no longer flowing around, and if there's no current flowing around, there will be no resistance opposed to current. Are we clear about that? So this is the first basic idea you should understand about the charging and discharging of the capacitor in the RC circuit, that is resistor and capacitor circuit. Are we clear? So basically what you take note of is that the moment your time is 0, your resistor has the highest voltage, that is 12 volts. But when it is fully charged, your capacitor would move from 0 to 12 volts. This is just in a literal context. So in some cases, your capacitor might have already had an existing voltage. So let's say it has maybe 3 volts, and you are asked to charge it to 12 volts. So depending. So it's not all capacitors that start from 0 volts. Are we clear about that? So, but once you know about the graph of your for charging the capacitor is, let us assume this is our voltage and it is 12 volts. Are we clear about that? Now, let us say let's assume we have a line here, this line for 12 volts. So since we are charging the capacitor, the maximum value of our capacitor will be 12 volts, right? So the voltage for our capacitor will rise from 0 to 12 volts. So, and here will be our time. So this is basically the simple graph for our charging of the capacitor, because your capacitor is being increased from the potential difference of 0 to 12 volts. Are we clear about that? That's the first basic thing you know when drawing the graph. Are we clear? Now to the formulas for the charging of the capacitor. So the charging of capacitor, the first basic formula is that your V, which is the final voltage that your capacitor would carry, is equals to the initial voltage into brackets 1 minus exponential minus T over CR. Are we clear about that? Now, this V, I said your V is the final voltage. Your V naught is the initial voltage. And it's very simple to calculate your initial voltage. So you know from Q is equals to CV, so you can just use your initial voltage to be equal to your charge over the capacitance. How you clear about that? So let's say for example they give the charge and they give the capacitance, you can just calculate initial voltage with charge over capacitance, or you do the current multiplied by the resistance. So you can either use your Q over C, or basically in some questions they will just give you the value for your initial voltage. So you can tell you that if a capacitor has a voltage of 24 volts and then it was charged to 30 volts, I don't care about that. So now our E is just the exponential function. Now our T is the time taken for the entire charging process. Now this CR is what we refer to as our time constant. CR is what we refer to as our time constant. How you clear about that? So it's just your time constant is the multiplication between your capacitance and your resistance. Very simple. So for the first basic formula that we'll be using here for charging of a capacitor is your V is equals to V naught into bracket 1 minus exponential minus T over CR. Are we clear? Another formula we have, so for your, it's also simple for your charge, your Q, that's your charge, is equals to Q naught. Now this Q naught you can also use, let's say they give the capacitance, they give you your voltage, you can use capacitance times voltage from Q is equals to CV to get your capacitance, sorry, to get your charge. Are we clear? So Q is equals to Q naught into bracket 1 minus exponential minus T over time constant. But for your current is I is equals to I naught exponential minus T over CR. There is no 1 minus whatever for your current. How you clear about that? So basically the formula for charging a capacitor, your V is equals to V naught to bracket 1 minus exponential minus T over CR. T is your time taken, CR is your time constant. Your Q is equals to Q naught to bracket 1 minus exponential minus T over CR. Your I naught is I is equals to I naught exponential minus T over CR. So those are the three basic formulas you know when you are trying to solve a question involving the charging of capacitors. When it comes to discharging of capacitors, so let's start with the graph first of all. So you notice the voltage. Let's say our voltage is, okay, let's say this is maximum voltage. That's the 12 volts from the diagram I gave earlier. So now since it's discharging now, discharging means that it's coming from that 12 volts down to the point of 0 in the basic idea. Are we clear about that? So the discharging of your capacitor would come from here, that's 12 volts, right? Eventually to the point of 0. So with your time. So this is the most simplest basic graph for your discharging of a capacitor. Are we clear about that? So now the formulas that are involved is very simple. So for this discharging of a capacitor, there is no 1 minus whatever. So for example, our V is equals to V naught. V naught. Okay, V is equals to V naught exponential minus T over C R. Straight up. Are we clear about that? So our V is equals to V naught exponential minus T over CR. Are we clear? So our now, mind you, for your current, so your current is also I is equals to I naught exponential T minus T over CR for your discharging. But take note, it is in the opposite direction. Because when you are discharging your capacitor, the current will have to move in the opposite direction. So basically, the difference between your, so except for this your current that has the same formula except for the direction, your voltage, also your charge, also is also Q naught exponential minus T over CR. So those are the basic formulas for the charging of your capacitor and the discharging of a capacitor in the basic simplest terms. So let us take some questions. This question, so this question is on charging of a capacitor. It says capacitor of capacitance 20 microfarad is connected in series with a resistor of 5 kilo ohm and a battery of EMF 12 volts. Find 1 the time constant, B. Charge on a capacitor after 0.5 seconds. C. The current after 0.05 seconds. So what the first thing we're looking for is the time constant. Now your time constant, I told you your time constant is equal to the capacitance multiplied by the resistance. But you can also call your time constant tau. You can also call it tau. That's like TAU. So our tau is equal to CR, right? So what's my capacitance? 20 microfarad. That is 20 times 10 raised to power minus 6 multiplied by what's my resistance? 5 kilo ohm. That's 5 times 1000. Am I correct? So my answer is so this give me 0.1 seconds. Now the unit for your time constant can also be in seconds. How you tell about that? So basically that's what it is. So this next question now says we should find the charge on the capacitor after 0.5 seconds. So since we know that our capacitor is charging because it said the capacitor of capacitor is connected in series with the resistor of 5 kilo ohms and the battery of EMF 12 ohms. So we are looking for the charge on the capacitor after 0.5 seconds. So that means that after 0.5 seconds, what is the charge that will be on the capacitor because it is currently charging. Not it's charging. Now we clear about that. So basically, what formula we're going to use? Our Q is equals to Q naught into bracket 1 minus exponential minus T over CR. Are we clear about that? Basically, from the formula for charging of the capacitor. And to calculate our Q naught will be equals to CV. Are we clear? So what is the capacitance given to us? That's 20 microfarad. That's 20 times 10 raised to power minus 6 multiplied by our voltage. Okay, that's EMF. That's 12 volts, right? So multiply by 12. So our answer would be, so we can say 2.4 times 10 raised to power minus 5 coulomb. So then we know that our time they give to us is what 0.5 seconds, and we already got our time constant as well, 0.1 seconds. So from here now we have um our Q, since that's the final charge we're looking for after 0.5 seconds, is equal to our Q naught is 2.4 times 10 raised to power minus 5 brackets 1 minus exponential. What is the time given to us? 0.5 seconds. So 0.5 over what is our CR? That's the time constant, 0.1. So from here we have 2.4 times 10 raised to power minus 5 brackets 1 minus. Now our 0.5 divided by 0.1 is 5. So exponential. So there's minus exponential minus 5. Are we clear about that? Minus 0.5 over 0.1 will give us minus 5. And exponential minus 5 will give us 0.0067. So from here we would have 2.4 times 10 raised to power minus 5 into bracket 1 minus this would give us 0.9933. We multiply this together, we have our final answer as 2.384 times 10 raised to power minus 5 coulomb. And that's our answer for the amount of charge on the capacitor after 0.5 seconds. Now let us calculate the current after 0.05 seconds. That we should look for the current after 0.05 seconds. So we already know that our time constant CR is 0.1 seconds. So now they give us our time to be 0.05 seconds. I know the formula we're using for the current is that our I is equals to I naught exponential minus T over CR. That's our time constant. Now to get our I naught, we'll use I naught is equals to V over R. How we care about it? Because those are the initial values they give to us about our capacitor. So from there, our velocity is, sorry, I said velocity, sorry, but our EMF, that's our voltage is 12, right? And it was our resistor was 5 kilo ohms, and no kilo is 1000, so that's over 5000. So present on our calculator, we would have 0.0024 amperes. So these are our value for our I naught. So we'll just input it here. So we have our current is equal to 0.0024 exponential. The time they gave to us was 0.05. So minus 0.05 over our time constant is 0.1 second. So from here we would have 0.0024 exponential. This give me minus 0.5 equals to 0.0024 multiplied by now exponential minus 0.5 would give me 0.6065. Yes. So we'll multiply everything together. We would have our final answer as 1.4 times 10 raised to power minus 3 ampere. So we can, since we know 10 raised to power minus 3 is milli, we can write our final answer as 1.4 times, okay, 1.4 milliampere. How do you feel about that? So this is, for example, how you would solve your questions when in cases where you are asked to look for the charging of a capacitor. Very simple. Just input the formulas. Our V is equals to V naught. Sorry, for charging of capacitor, V is equals to V naught into brackets 1 minus exponential T minus T over CR. V is equals to V naught into brackets 1 minus exponential minus T over CR. But your current does not have a minus for both cases. But I told you that in discharging, the current would be moving in opposite direction, so it will be minus. But you don't need to put the minus, but you can just put that explain later when solving the theory on that. Let us solve one question now on discharging of a capacitor. The discharge of a capacitor. So the question says that a capacitor of capacitance 50 microfarad is charged to a potential difference of 24 volts. It is then discharged through a resistor of resistance 20 kilo ohms. Find the current in the circuit after 5 seconds. This is a very simple question. The only thing we're looking for is the current. So it's still the same formula we're going to use, just like we did earlier. So the first one we'll calculate our time constant, which is our tau. I know that our tau is equals to capacitance multiplied by resistance. And our capacitance is 50 microfarad. That's 50 times 10 raised to power minus 6 multiplied by our resistance is 20 kilo ohms. That's 20 times 10 raised to power 3 ohms. And from there, we multiply that together, we would have our answer to be 10 seconds. So I told you that our tau is 10 seconds. So now that our tau is 10 seconds, we know the formula to use for the current is that our I is equals to I naught exponential minus T over CR. And I told you already that in the case of your current, when it is discharged, because I said it is discharged through the resistor. When your capacitor is discharged, your current will move in the opposite direction, so this is the minus. So to get our I naught is equals to V over R, and our voltage they gave us there was 24, but the resistance is 20 kilo ohms. That's 20,000. So we would have 1.2 times 10 raised to power minus 4 ampere. Yes, so 1.2 times 10 raised to power minus 4 ampere. So this is our initial current. Okay, so we'll just put in the values. So we have my I is equals to, doing the minus. The minus is just to tell you that the direction is the opposite side. So my I naught is 1.2 times 10 raised to power minus 4 exponential minus my time is 5 seconds over my time constant is what, 10 seconds. So my I will be equals to 1.2 times 10 raised to power minus 4 exponential 5 over 10 is 0.5, so that's minus 0.5. So we have I is equals to 1.2 times 10 raised to power minus 4. Now exponential minus 0.5 is 0.6065. You can find that on your calculator. And we even used this in the previous question. So once we multiply together on our calculator, we are going to get 7.28 times 10 raised to power minus 5 ampere. Very simple. So this is very simple on the discharging of a capacitor. Just very simple, a straightforward mechanism, straightforward method on discharging of a capacitor. So the formulas are very simple and straightforward. Also understand the graph. So in case they ask you questions about, you have to draw the graph in theory-based cases. Next part of the charging and discharging of a capacitor that we refer to as the half-life. So the half-life is the time required. Half-life is the time required for the capacitor to reach to the half of the initial charge. Are we clear? So let's say, for example, let's say the initial charge should be 12. So the time for the capacitor to reach a charge of 6, that is the time. That time is all referred to as the half-life. Are we clear? So, and there's just a very simple, straightforward way to get to half-life is that your half-life in the charge of the capacitor is equal to 0.693 multiplied by your tau. That's your time constant. Are we clear? So the way I for the half-life, your half-life is equal to 0.693 multiplied by the tau. That's our half-life. Are we clear about that? So straightforward. It's just the time taking for the capacitor to attain a charge that is half of the initial charge. Are we clear about that? And there's also a very common question they ask, whereby they ask you that how many time constant is required to, sorry, how many time constant is required to attain a to completely charge the capacitor. Yes. So the answer is actually 5 time constant, 5 CR. How? How do we attain that value? Let us say, for example, we have a table. Let's say we have a table, for example, like this. Let's put our time in. So when our time is 1 second, that is 2, 3, 4, 5. Are we clear? Um, so now from basically, let's say let us take our voltage, for example. You know, our V for charging, our V is equal to V naught into bracket 1 minus exponential minus T over CR. Are we clear about that? So if we take a practical case and we put our time as 1 second, 2 seconds, 3 seconds, 4 seconds, and you place the value of CR, subsequently what you'll be getting is that at this point 5, you would have 99% would attain, about 99% of the capacitor would almost be charged up. So that means that whenever it's a very common question, whenever they ask you a question that's how many time constant is required for the capacitor to be fully charged, which is 5 time constant, that is 5 CR. So about 5 CR is not 100%, around 5 CR, 99% of the capacitor is fully charged. So from this, I would okay, so the next aspect of moving to the current electricity on A-level physics. So this is just basically majority of the greatest phenomenons on charging and discharging the capacitor. Ensure you like, ensure you subscribe, ensure you comment. Thank you for watching.
For more videos, visit our website at okotorilearn.web.app.